This lesson's about the word work. It is a simple sounding word, but in the context of physics, we have to be very thoughtful about what work can mean. Let's start with the bottom of this slide. In order for work to be done, a force has to be exerted through a distance. Now that force has to be parallel to the distance. So if something is pushed to the right and it moves to the right, or even if it's pushed to the right and it moves to the left, as long as the force and distance through which the force is exerted are parallel, work's going to be done. But what happens when work is done can be different. Work literally is a change in energy. But of course, different forms of energy exist. So when work is done, different forms of energy might change. So let's say that something was pushed with a force so that it went faster. That would change the object's speed, which means the type of energy that exists or that's different after that push would be a change in kinetic energy. So while we could calculate the work with force times distance, if we knew the mass and the speed of the object before and after, so VI before, VF after, we could calculate 1/2 mass times VF squared. That would be the kinetic energy at the end, EK final, and subtract off 1/2 MVI squared. That would be the kinetic energy at the start. Well, that's the difference in energy, so that's how much new energy there would be. Whether it was more or less depends on whether we cause the object to get faster or slower with our force. What that means is literally there is many ways to calculate work depending on the situation. It always gets done with force times distance, and so that's always a possibility of how it could be calculated. But there's many times where we don't know what the force was and we don't know what the distance was. And in that case, we have to think about this slide to think about how that work became a new kind of energy. In the case of kinetic energy, we can do what we just talked through. The difference in the kinetic energy before and after is the work. Well, of course, not all work is done to make something go faster. Some work is done to lift something. So potential energy due to gravity is equal to m times ag times dy, the height. Of course, that triangle, delta, means change in whatever comes next. So in this case, delta dy means the change in the height. So if something is lifted 4 meters higher than it was, the only way that can be done is if work is done. And so we can calculate the work with the average amount of force, m times ag if you're lifting something, times how much higher it is. Now, of course, if we think about it from gravity's perspective, when it's pulled back down, gravity does that same amount of work, and that's where the kinetic energy comes from. So if we lift an object, we might calculate the gravitational potential energy difference from where it was to where it ends up, and that would be the work done. Now, of course, if we stretch a spring, then the energy stored in a spring is equal to the average force while stretching or compressing it times how far it was stretched or compressed. So we would calculate that, and that is the work. So regardless of what actual change the work caused, there's no way for work to be done without pushing through a distance. No way to make something go faster unless there's a net force exerted on it to cause it to accelerate. No way to lift something unless there's a net force upwards to start it, to get it moving upwards, and then that force has to be continually applied to cancel out gravity as it's lifted. Then, after average times distance, no way to stretch or compress a spring unless that spring has force exerted on us. So, regardless of what kind of work, what kind of energy the work ends up being, it always takes a force exerted through a distance to cause it. The key to this slide is recognizing we don't always calculate the work that way. We oftentimes calculate the work by calculating how much new kinetic or gravitational potential or spring potential energy exists after the work is done compared to before the work was done. Now, of course, sometimes energy can become more than one form at a time. So let's take a look at this slide and think about that. What if the work is done and the work results in a change in more than one form of energy? Well, you'll be relieved to know that energy is not a vector right there. So we don't have to draw any triangles about energy. All right, energy is not a vector. Yay! We can just simply add and subtract it. Now, what you've got here is somebody shooting a free throw. So the person's crouched down, the ball's down low, and they're about to push on it that way. So from the basketball player's perspective, he moved it this distance and did F times D. But we don't know how hard the basketball player pushed it, and we don't really know how far he pushed it since he pushed it at an angle. So while he did work with F times D, that in this case isn't how we could calculate the work done. What we could do instead is analyze what kind of energy exists because of the work that he did. Well, the ball ends up higher when he releases it compared to when he started pushing on it. Since it's up higher, there's a change in height, which means he lifted it, so some of the work is gravitational potential energy. Now, because the ball wouldn't have any speed here, there'd be no kinetic energy. Of course, when he releases it, he hopes it doesn't just fall straight there. It must have some velocity to try and go on towards the hoop and then go in, so the ball has speed there. Since the ball gained both speed and height, then it must have gained kinetic energy to have that speed, and it must have gained gravitational potential energy in order to be up high. So in that case, the work done is equal to the gravitational potential energy that's new and the kinetic energy that's new. So gravitational potential energy is mass times ag times dy, and what we'd put in here would be the change in height. Only the dy between where it started and where it ended. Its actual height is irrelevant because he only did work to lift it through the height difference. And we'd add on 1/2 mv squared, that's the kinetic energy. Now I've left off the subtraction of 1/2 mvi squared. We only have to do 1/2 mvf squared because vi was 0. So all the kinetic energy when he releases it is all work because it didn't have any kinetic energy to start. What we want you to see from this situation is that oftentimes the work done isn't findable by just finding one form of energy. You'd have to find all the new energy that exists from before to after. That's an important moment too. You notice that we didn't really think about what was happening along the way as the ball moved. We really thought about this moment right before he started giving the ball speed and height, and this moment right when he released it. With energy, we oftentimes care about moments in time. And so 1/2 mv squared, we're never going to put average velocity in there because we don't really care about how much energy something had on average. We always care how much energy something has at a moment. So let's do a practice problem about that issue. A 75-kilogram man starts from rest at the bottom of a staircase. He runs up the stairs as fast as he can, reaching a height of 3.5 meters. When he gets to the top, he has a velocity of 2.9 meters per second. How much work did he do? So we've got a set of stairs. We know that set of stairs is 3.5 meters high. We also know that, at least to start with, the man is standing at the bottom of the stairs with Vi of 0. Now, when he gets to the top of the stairs, here the Vf is 2.9 meters per second. So let's compare beginning to end. Again, we don't really care that much about along the way. With energy, we always care about moments in time. So I'm going to call this moment A. The first moment he starts climbing the stairs, and I'm going to call when he gets to the top moment B. So in between A to B, how much work did he do? Well, from A to B, he ends up higher. There's a change in dy. Now, where this actually is in terms of altitude from Earth, I don't really care that much. It's the difference in height that means he had to have done work. Basically, I'm calling the lowest spot an object is in a problem dy equals 0. We can reset wherever the ground is locally to the lowest height possible. So since he ends up higher, I know there's a gain in gravitational potential energy, and any change in energy is work. Now, he also wasn't moving, and then once he gets to the top of the stairs, he is. So that means he has new kinetic energy since he's going faster, and kinetic energy is related to speed. That is also work. And since both forms of energy are new, in other words, there's more of both, if we add them together, we get the total change in energy. Now, in this case, we would call that mechanical energy because kinetic and gravitational potential and elastic spring potential energy are all just different forms of mechanical energy, and a change in energy is work. Now, that means that we can calculate that work with how much new gravitational potential energy is there plus how much new kinetic energy is there. We don't have to worry about spring potential energy because he didn't stretch or compress any material on the way. So there isn't any spring potential energy related. That would be the change in mechanical energy, which is the work. And now we substitute in what that's equal to. Gravitational potential energy is m times ag times dy. Kinetic energy is half times mass times velocity final squared minus the initial kinetic energy, 1/2 mvi squared. Vi was 0, so this term will drop out. And we can plug in the values. He's got a mass of 75 kilograms. That times 9.81 meters per second times the new height of 3.5 meters. There's the gravitational potential energy. Plus his new kinetic energy, 1/2 times 75 kilograms times 2.9 meters per second. Only the 2.9 meters per second gets squared. Once we find both forms of energy, then we can add them together to get the total work done. Now, when we type that into our calculator, we find that the new gravitational potential energy is 2,575 and an eighth, 0.125. This would be in joules, kilogram meters squared per second squared. The new kinetic energy is only 315.375 joules. So it takes much more energy to get to the top of the stairs than it does to get going faster. And this is not uncommon. This is why cars can get pretty decent gas mileage when they're just driving along on a flat stretch of road. But you really have to lay into the gas to be able to get your car to drive uphill. Conversely, if you've ever gone up to the mountains skiing, when you come back from the mountains, you barely have to touch the gas at all. You can just coast down because once you're already at the top of the hill, your gravitational potential energy can be converted into kinetic energy and help you overcome friction as you slide down. If we add these two together, we end up with a total new energy of 2,890.5 joules. We only had 2 sig figs in our given, so we would round that to 2,900 joules of energy. Now, if you're thinking, man, what a great way to lose weight, a couple of things you need to know. One is that 4,186 joules equals 1 kilocalorie, 1 food calorie. In other words, running up the stairs like this only burned a little less, maybe about 3/4 of a food calorie. So your average Snickers bar might be 200-300 calories. You'd have to do this 300 times to burn off about 225 calories. So that's why it takes so much exercise to counteract eating a little bit more food than your body needs to maintain its equilibrium. So the last thing we want to make sure we talk about before we move on from the idea of work is back one slide. And let's go back there. There are other forms of energy. If we drag something across a level floor, let's say that we have a box and it's sitting on the floor and it's too heavy for us to lift. So we hold on to it and we drag it across the floor and it ends up over here. Well, we are certainly a force that way. And then we move it through a distance in the same direction. By that definition, we did work. Except it's at the same height. So there's no change in gravitational potential energy. It's not elastic, so we didn't stretch it or compress it. So there's no spring potential energy. And if the velocity here at the start was 0, we drag it across the floor and we leave it there. So the final velocity is also 0. That means we didn't change its kinetic energy from start to finish. I mean, yeah, it was moving in the middle, but remember, energy is about moments in time from the start to the end. Well, what that means is that the net force on the box was actually 0 the whole time, and the force that we exerted was really to overcome another force, and of course, that force that we're overcoming happens between the bottom of the box and the floor. It's friction. And whenever we overcome friction, we still have to do FD to do it, but work done to overcome friction doesn't become a useful form of mechanical energy like kinetic energy or gravitational potential energy. That work becomes thermal energy, better known as heat. So we might warm up the bottom of the box a little bit. Now, measuring the heat or calculating the heat is nearly impossible. So that's one reason why work force times distance is a very useful way of calculating the work done to overcome friction. So be careful. Every once in a while, you're going to see a situation where work was done, but the work doesn't end up turning into one of these useful forms of mechanical energy. And in those cases, watch that red flag and think about whether or not maybe some work was being done to overcome friction. And in that case, that's where the F times D went. All right, you're ready to try some problems about work, a change in energy.